Hey everyone, this is Dr. Walker. This is video 90 on standing waves. I want to start this video by showing you a little clip of a standing wave because it's hard to explain, it's easier to show it. So what we have here is we're going to have one red wave here traveling to the right, and then the blue one is going to be the reflected wave. Imagine that there's some kind of boundary here and the wave is reflected. And this blue wave is going to travel to the left. Let's see what happens. So you can see that the result that happens here is this purple wave, and it appears to be standing still, right? It doesn't appear to be moving left or right, it just appears to be moving up and down. And this is because of constructive and destructive interference that happens when these two waves combine. So let's take a look. So standing waves are set up by continuous superposition of incident and reflected waves. That's what we just saw. Now we could set this up in a string. We can flick the string here and we flick it at the right frequency and we'll see one incident and one reflected wave. What we'll see here is called a node. This is a region of maximum displacement, and then an antinode on each end. Sorry, I got that backwards. The antinode is in the middle. That's the region of maximum displacement. At each end, we have the nodes, which are regions of zero displacement. Depending on how quickly you flick your wrist, you will start to see different patterns with more and more antinodes and nodes. These different patterns that we see, they're called the normal modes of vibration. So each string that has a certain length will have these patterns of vibration called normal modes. The first pattern, we say n is equal to 1. This book uses m, but I like to use n, so just pretend all of these are n's. And then what distinguishes each pattern from the next one is that each successive one has an additional antinode. You can see this one has one antinode, this one has two, this one has three, etc. Let's look at the frequencies of these normal modes of vibration. First, let's look at the wavelength. It's easier to see. Remember that our string here that is fixed at both ends has a length L. If we look at the first mode of vibration here with n is equal to 1, we can see that this here is only half of a wavelength because a full wavelength would look like this. So this means that L is equal to 1/2 of the wavelength. So that means that the wavelength is equal to 2L. For the next one, we can see that we have a full wavelength. L is equal to the full wavelength. That means that the wavelength equals L. So to get the expression for each consecutive wavelength, we have this expression, 2L over n. And we can see that it makes sense by just counting how many wavelengths we have for each normal mode of vibration. Now what we're usually more interested in, instead of the wavelength, is the frequency. Frequency is speed divided by wavelength, so just take the speed and divide it by this expression. These frequencies that we get for each normal mode of vibration is called the natural frequency. It's also called harmonics. You may have heard about this if you've played any kind of instrument. So these standing waves formed on strings. Why do we care about them? Well, if you've heard of any stringed instruments, they're producing these standing waves, and that's what produces the different sounds that we hear. Now, standing waves can also be set up in air columns. Instead of the string interacting with each other, right, the incident wave interfering with the reflected wave, you're going to have sound waves interfering with each other. But in this video, I just wanted to kind of touch upon standing waves and let you know what that possibility was. But I did not want to get into all the details of also looking at standing waves and air columns, especially since we haven't discussed sound yet. So this was just a brief introduction to standing waves.